Okay, so it will be a brief complement to what I said this morning. As you might have noticed, I did not mention the results on the early universe cosmology, and so briefly. The Planck results for that is obviously detecting the deviation from the scale invariance and the deviation from ns equal 1. And the number we are now, which are new numbers, but they are not much different from the others, is, as you see, basically almost 8 sigma from 1. So deviation is even better established than in the 2015. And when you introduce curvature, basically you find something which is compatible with 0. Now, Planck alone has not enough sensitivity in the beam in the low L, although we clean very well, as I showed this morning, the very large scale and well enough to get a very good number for the tau number, the reionization parameter. On R, basically, we are limited by, we don't do as well when looking at the B modes. In fact, the best number is given by the TT, and it was 0.1 in 2015, and that has no reason to change much in 2018. And as you know, we had a collaboration with the Bicep Keck collaboration. They asked us to basically do the correlation of their data on the B modes with the dust map at 353 gigahertz. And I just want to recall that and tell you what I think the future of the 353 gigahertz is for contributing to that. Well, that's the map, the polarized, it's a map of the magnetic field on the whole sky from the polarized maps. And just as an illustration of what happened on the Bicep field, so you could see the Bicep field with this white area. And just by eye, you can see that basically we can reconstruct the field lines very well. And in region where we don't detect the polarization of the dust, we cannot. So it's just basically an obvious demonstration that we detect very well the dust and the E modes which are associated with it. And so, as you probably remember or know, we got, after removing the dust, on the power spectrum, you have in black the raw data, and the blue points are the data, the Bicep Keck data after removing the 353. And so basically it's fully compatible with the lensing, which is not detected very well, but which is there. So that led to the number I quoted above, and I repeat here the parameter R is at 95% confidence, 0.08 if we combine just TT and the polarization data from the low frequency instrument. And if we add to that the lensing and to that, and of course the Bicep thing, it's comparable, not even just, it rises a bit to 0.09. So basically the NS R plane is represented there in the paper we published with them, and which shows basically that we could rule out a number of inflation model, and so that's where we were. And from that point of view, we will not be much further, as I said, because what we improved was the polarization at very large scale, but that's not what was driving this result. Coming to my second point, I show again the 353 gigahertz and the null test we do. So you can see the dust spectrum, which is basically the cross spectrum between, for example, two half missions, and E modes, B modes. And you could see that in 2015, the difference associated with the same two maps are white noise, but basically it was rising very, very steeply. For example, if you take the difference between two detector sets. And now we are with the rise, which is basically a factor of 2 to 3 above the white noise for both E modes and the B modes. So that's the situation, and I showed you also some other evidence by looking at the odd-even surveys when we scan the sky in two different directions, and of course you see very well the influence of the time constant or the far side lobes, and you could see that there is an obvious pattern between the odd and the even surveys. So we need to clean that better. And if we clean that as well as we did for the 100 and 143, we would hopefully become very, very close to the white noise. So the question we ask ourselves is, if we can do that, what would be the R value, or the minimum, or the noise value we would get if ground-based instruments which are being developed and that Lyman is going to talk about, if they are going to be much better than the Planck data quite soon, and if they need to use for large pieces of sky Planck, what is the limit which is going to be put by this use of the 353. So this is just a very simple model, assuming that you have 150 or 100 gigahertz data without noise or negligible noise, and you combine that with the 353, and you look at the posterior distribution, and you do that for 3 sky fraction, 10%, 30%, 50%. And you do that on the recombination peak for the B modes. So that's the meaning of the L, minimum L, which is associated with that, which is 30. So you could see basically that for the full sky, you have the blue line there. Now, we also looked at combining that plus with the same white noise, combining that with the realization peak. And so we go down here. So that would be basically posterior, and you could see that basically if you do a 95% or 98% confidence, you get typically in the regime of the 2 to 3, 10 minus 3 in R. Thus, being able to detect properly 10 minus 2, which is not exactly in the long range goals for this ground-based experiment, but at least for some years, I'm sure that basically the 353 data from Planck will still be used. So I will stop with that and leave the floor to Laima, except if there are questions on that. More question?
Is there any question for Jean-Loup?
One more remark. So,
Yes.
obviously, that means that the Planck collaboration is basically stopping with this release, which will be done in a little bit more than 1 week. But we are going to try. We are going to do this cleaning of the 353, and when it's done, it will be open to collaboration. And